What's up guys, this is Demkeys and today I'm going to teach you about Mathf.PerlinNoise. Now usually I like to jump right into the tutorial, but in this case I'm going to have to give you a little bit of an explanation, so just bear with me. I'll try and keep it as short as possible. So let's talk about Perlin Noise in general. The algorithm was made by a guy called Ken Perlin. Among its many other uses, it is also very commonly used in CGI for procedural texture generation, making visual effects, and so on. How the method works is, it takes in a position and returns a pseudo-random value usually between -1 and +1. I'll explain the pseudo-random part a little bit later. Perlin noise can be implemented in more than just one dimension, so it could be 2-dimensional, 3-dimensional, or more. The number of coordinates that you have to pass in as arguments will depend on the type of implementation. So for example, if you are implementing 3-dimensional Perlin noise, you will have to pass in 3 arguments, x, y, and z. If you're implementing 2-dimensional Perlin noise, you'll have to pass in 2 arguments, x and y, and so on. Now I'm not done explaining exactly what this method does, but I'm going to shift the explanation into Unity. So Mathf.PerlinNoise implements 2-dimensional Perlin noise. So it takes in 2 arguments, x and y, and in this case it returns a pseudo-random value between 0 and 1. That's just the way that they have implemented it. So what is the relation between the position being passed in and the value being returned? To understand this, let's create a simple Perlin noise generator. Right click in the hierarchy, click create empty. This is going to create an empty game object. Rename it to Perlin Gen and add a new script to this game object. Let's call it Perlin Gen script 01. Open this up in MonoDevelop. Now this is going to be a really simple script. We just need 2 variables, public vector 2 Perlin position and public float Perlin noise. In the update method, type Perlin noise equals Mathf.PerlinNoise. So we are calling the Perlin noise method here. And as you can see, this method takes in 2 arguments, x and y. So we are going to pass in Perlin position.x and Perlin position.y as arguments. That's it. This is our script. Hit save. And real quick, let me explain what's going on over here. So we have 2 variables, public vector 2 Perlin position and public float Perlin noise. In the update method, we are calling Mathf.PerlinNoise, and as you can see, it takes in 2 arguments, x and y. We are passing in Perlin position.x and Perlin position.y as the arguments. Whatever value is returned by the Perlin noise method is going to be stored in the Perlin noise variable, and this is a public variable, so we are going to be able to read this value from the inspector. We will also be setting the values for Perlin position.x and y from the inspector. So go back to Unity and hit play. Alright, so as you can see, from the very beginning, the Perlin noise method is giving out a value. This is the value that is returned when you pass in the coordinates 0 on x and 0 on y. We'll discuss this a little bit later, but for now we are going to use other positions. Now, since we are dealing with 2-dimensional positions, it would help if you were able to visualize these positions on a 2-dimensional grid. So I'm going to bring a 2-dimensional grid up on the screen, and each time we enter a position's coordinates into the Perlin noise method, I'm going to show that position on the grid. So this is our 2-dimensional grid. Now let's say we have 2 positions, position A and position B, and let's say position A's coordinates are 2.814 on the x-axis and 4.552 on the y-axis. Let's enter these coordinates into the Perlin noise method and see what result we get. So that's 2.814 on the x-axis and 4.552 on the y-axis. As you can see, the result returned is 0.6775. Now let's say position B is very close to position A, and position B's coordinates are 2.836 on the x-axis and 4.552 on the y-axis. So let's pass these coordinates into the Perlin noise method and see what result is returned. So that's 2.836 on the x-axis and 4.552 on the y-axis. As you can see, the result returned is 0.6724. Now notice something here. Both these positions are very close to each other, and when the coordinates of both of these positions were passed into the Perlin noise method, the 2 values that were returned are also very close to each other. Alright, let's try this again. Let's say we have 2 more positions, position C and position D. Position C's coordinates are 6.947 on the x-axis and 2.809 on the y-axis. When you pass these coordinates into the Perlin noise method, the value returned is 0.5856. Now let's say position D's coordinates are 6.962 on the x-axis and 2.781 on the y-axis. When we pass these coordinates into the Perlin noise method, the value returned is 0.6002. Now even over here, notice how both these positions are very close to each other, and the Perlin noise values returned are also very close to each other. Now real quick, I want to mention, I know that these positions are not placed accurately on the grid. The whole point of showing you the grid was not to place the positions accurately. The whole point of showing you the grid was to give you an idea of the distance between these these positions. Okay, so back to what I was saying. This here is exactly what the Perlin Noise method does. Alright, now let me explain a couple of characteristics of the Perlin Noise method. First of all, close positions return close values. You can see this perfectly in our earlier examples with position A and B and position C and D. Next, the return value will almost always be between 0 and 1. Again, this is just how they have implemented the Perlin Noise method. It almost always returns a value between 0 and 1. I'm saying almost always because there's a very rare chance that the value returned by the Perlin Noise method might be slightly below 0 or slightly above 1. Of course, there are ways around this. For example, you could clamp the value between 0 and 1 using Mathf.clamp. Next, the values returned are pseudo-random. Now, what does pseudo-random mean? Pseudo-random basically means that it appears to be random, but it's not really random. The value is actually being generated using some sort of mathematical algorithm. Next, Perlin Noise is very predictable. Basically what this means is any two coordinates that you pass into the Perlin Noise method will always return the same value. Let's say, for example, we pass in the coordinates of position A. So that's 2.814 on the x-axis and 4.552 on the y-axis. As you can see, the value returned is 0.6675. You can pass these same coordinates into the Perlin Noise method multiple times and you will still get the same value. That's what makes Perlin Noise very predictable. Any two given coordinates will always return the same Perlin Noise value. And the final characteristic you need to know about is that you cannot pass in whole numbers. So this brings us back to the whole situation with passing in 0 on x and 0 on y. So as you can see, when you pass in 0 on x and 0 on y, the value returned is 0.4652. Let's try changing these numbers. Now keep in mind, do not add any decimal point after either of these numbers. Just keep changing them to other whole numbers. 0, 5, 10, 2516, and the same thing goes for y as well. You could change it to something like 8597. As you can see, the value is still the same. You can pass in any two whole numbers and they'll still give you the same value. This has something to do with the way that the Perlin Noise algorithm works. You cannot pass in two whole numbers because you're always going to get the same value. In order to get a different value, you have to use decimal numbers. Either one of these numbers has to be different. So as you can see right now with these coordinates, the value being returned is 0.4652. But let's say I change the value to 25.16. Suddenly we have a different value being returned. So the basic idea is that you cannot pass in two whole numbers and expect to get a different result. Either one of the numbers or both of the numbers have to be decimal numbers. So some sort of float numbers like 2.754 and 9.345. This gives you a different value. Alright, so now that I've explained exactly what the Perlin Noise method does and I've told you about the various characteristics of the Perlin Noise method, I'm going to show you 3 examples. These are definitely not the only 3 ways that you can use Perlin Noise, but hopefully these 3 examples will give you some ideas of how you can use Perlin Noise. So stop the game and right click in the hierarchy, click 3D object, cube. This is going to create a cube in our scene. Add a new script to this game object, call it Perlin Move Script 01. Open this up in MonoDevelop. Alright, so this is also going to be a really simple script. We're going to create a bunch of variables. Those variables are only being created so that you can see the values changing in the inspector. So type public float elapsed time and public float Perlin Noise. In the update method, type elapsed time equals time.time. Time.time is basically the amount of time that has passed since the game started. So pretty much every frame this value is going to be changing. Next, type Perlin Noise equals Mathf.PerlinNoise, and here we are going to pass in elapsed time as our x coordinate and 0 as our y coordinate. Now remember what I told you earlier, both the numbers cannot be whole numbers. Either one of them has to be a decimal. So in this case, that is our elapsed time value. I just remembered there was one more variable that I forgot to add. That's public float multiplier. Now in the update method, type transform.position equals new vector 3. We want the position on the x-axis to remain the same. On the y-axis, we want the position to be Perlin Noise multiplied by multiplier. And we want the position to stay same on the z-axis. So that's transform.position.z. Hit save. I don't think I need to explain this any further because I've already explained what's going on over here. So let's go back to the editor, and before you run the game, change the position to 0 on all axes. This is something I forgot to do earlier. And as you can see, our game object is far away now. So with the game object selected in the hierarchy, either double click the game object or hit F on your keyboard and the editor will zoom into the game object. Alright, one last thing to do is to select this directional light and drag it down so it's not obstructing our view. Now select the cube game object, and under our Perlin move script 01, set the value of multiplier to 5. You don't need to set the values for elapsed time or Perlin noise because both of those values are handled by the script. Hit play. As you can see, the object seems to be moving up and down in a very smooth motion. There's no choppiness being shown in the motion, and the reason is that we are using elapsed time as the x coordinate for our Perlin noise method. As you can see, these are the Perlin noise values being generated each frame. Then because these values are so small, they are being multiplied by the multiplier value, and then that value is being set as our game object's y position. Now, to understand why this sort of smooth motion is there, think of it like this. I'm going to pause the game, and each frame, look at the elapsed time value. As you can see, there's not a very big change in the elapsed time value. It's a really small change. So now I want you to visualize this on a two-dimensional grid. Just imagine that on the x-axis you have a position 47.12, and in the next frame that becomes 14, 16, 18, 20, and so on. Because these positions are so close to each other, the pseudo-random values being generated are also very close to each other. So that's our first example. On to our next example. Let's disable both these game objects, Perlin Gen and Cube. Right-click in the hierarchy, click create empty, and rename this game object to cube gen. Add a new script to this game object, call it Perlin cube gen script 01, and open it up in MonoDevelop. Now this is going to be a slightly more complicated example than the others, but I'll try and keep it as simple as possible. First we need to create our variables, so that's public float Perlin noise, public float refinement, public float multiplier, and finally public int cubes. So in the start method, type for int I equals 0, I less than cubes, I plus plus. Within that for loop, type for int j equals 0, j less than cubes, j plus plus. And within this for loop, type Perlin noise equals Mathf.PerlinNoise, I multiplied by refinement on the x-axis and j multiplied by refinement on the y-axis. Next, type gameObject go equals gameObject.createPrimitive, primitive type .cube. This is pretty much going to create a cube game object for us. Then type go.transform.position equals new vector 3, I on the x-axis, Perlin noise multiplied by multiplier on the y-axis, and j on the z-axis. I think that's about it. Hit save, and real quick let me explain what's going to happen over here. So we've got 4 variables, Perlin noise, refinement, multiplier. All 3 of these are float variables, and the final one is cubes, which is an int variable. And in the start method we have 2 for loops, this, and within this for loop we are setting the value of Perlin noise, and the arguments being passed in are I multiplied by refinement and j multiplied by refinement. Now the reason we are multiplying these values by refinement is because by themselves these values are always going to be whole numbers. As you can see, they are integers, and so they are always going to be whole numbers. They're never going to be decimals, and if you remember, I had explained earlier that you cannot pass in 2 whole numbers into the Perlin noise method and expect to get different values every single time. So because of that, we are multiplying I with refinement. So for example, if the value of refinement is 0.1, then when I is 0, 0 will be passed in as the x coordinate. When I is 1, 0.1 will be passed in as the x coordinate, and so on. And the same goes for the y coordinate as well. Next, we are creating a primitive game object, pretty much a cube, and finally we are setting the position of this cube to I on the x-axis, Perlin noise multiplied by multiplier on the y-axis, and j on the z-axis. And let's see the result of that. Hit save, go back to Unity, and let's set the values for our variables before running the game. So refinement has to be 0.1, multiplier has to be something something a little high, maybe 10, and cubes has to be 50. Keep in mind, the total number of cubes that you're going to see are 50 multiplied by 50, because if you see over here, we have two for loops, and each one of them is going to run for whatever the value of the cubes variable is. So since it's running twice, so 50 multiplied by 50 is 2500. So we're going to have 2500 game objects being created, and each one of their positions is going to be set according to this statement. So let's run the game and see the result. As you can see, this is the result. Now again, let's try to visualize the grid over here. So let's start with the first game object. That's 0 on X, 4.6527 on the Y-axis, and 0 on Z. The next game object is 0 on X, this value on the Y-axis, and 1 on Z. Then the next, and next, and next. If you notice, one thing that they all have in common is that all their positions, specifically only on the Y-axis, all their positions are very close to each other. So this is another good example of how the Perlin noise method works. So this is example number 2. Alright, so for our next example, we are going to generate a whole bunch of Perlin noise values, store those values into a multidimensional array, and then use that multidimensional array to set a terrain's height data. So right click in the hierarchy, click 3D object, terrain. That's going to create a terrain game object for us. This terrain is way too big, so with the terrain game object selected, under the settings tab, under resolution, set the terrain width to 50 and the terrain length to 50 as well, and make sure that your height map resolution is 513. I'll explain why a little bit later. Add a new script to this game object, call it Perlin terrain script 01. Open this up in MonoDevelop, and now let's create our variables. So type public float. This is going to be a multi-dimensional array, so square bracket comma square bracket. We're going to call this terrain height data. Next, public int rows and columns. This is basically going to set the size of our multi-dimensional array. Next, public float refinement. You already know what this does. Then public float multiplier. You already know what this does as well. Float Perlin noise, and terrain. So Perlin noise is basically the variable in which our generated Perlin noise value is going to be stored, and terrain is going to be a reference to the terrain component of this game object. In the start method, type terrain height data equals new float, and we need to specify the size, so that's rows and columns and rows and columns. Then terrain equals get component terrain. Then for int I equals 0, I less than rows and columns, I plus plus. Then for int j equals 0, j less than rows and columns, j plus plus. And then within the for loop, type Perlin noise equals Mathf.PerlinNoise, I multiplied by refinement, j multiplied by refinement. Next, type terrain height data I j equals Perlin noise multiplied by multiplier. And finally, at the end of the start method, type terrain.terrainData.setHeights. As you can see, this method takes in 3 arguments: x base, y base, and heights. So x base is going to be 0, y base will be 0 as well, and heights will be our multidimensional array, which is terrain height data. Hit save, and real quick let me explain what's going on in this script. So in the start method, first we are initializing our multidimensional array and setting its size. Next, we are storing a reference to the terrain component of this game object, and then we have a nested for loop, and within the inner for loop, we are first generating a Perlin noise value. I'm not going to explain this part because you already know this from the previous example, and whatever value is generated, we are storing that value in the Perlin noise variable. Then we multiply that Perlin noise value with multiplier and store the result into this cell of our multidimensional array. Finally, we call terrain.terrainData.setHeights. Now, I won't go into full detail about how this method works because that goes beyond the scope of this tutorial, but I will give you a fair amount of information so that you don't get errors while messing around with different values. So before I explain this statement here, hit save, go back to the editor, and let's see the result of our code. So let's first set the values for our variables. Rows and columns should be 513, refinement should be 0.01, and multiplier should be 0.01 as well. Hit play, and as you can see, the height data for our terrain has been set using the Perlin noise values in our multidimensional array. Alright, now let me explain how the set heights method works. So with the terrain game object selected, click on the second tab under the terrain component and click flatten. This is going to flatten our terrain. Okay, so as you can see, the set heights method takes in 3 arguments: x base, y base, base, and heights. Heights is basically the multidimensional array that contains the data that is meant to be used when setting the height for the terrain. The value has to be between 0 and 1. Now, x base and y base basically tell this method where to start setting the height from. So currently, x base is set to 0 and y base is also set to 0. So it starts setting the data from this area. And since our multidimensional array's size is 513 by 513 and our terrain's height map resolution is also 513 by 513, when we start setting the data from 0x base and 0y base, it sets 513 in this direction and 513 in that direction, and it works out perfectly fine. However, let's say I set x base to 100 and y base to 100 as well. Hit save, go back to Unity, hit play. As you can see, I'm getting an exception here that says x or y base out of bounds, setting up to 613 by 613 while map size is 513 by 513. So if you remember, our height map resolution is 513 by 513. Basically what happens is when you set x base to 100 and y base to 100, 100 on x and y is roughly around this area. So it's going to start setting heights from this point on in this direction and that direction. So that's 513 in this direction and 513 in that direction. And since you're starting from this point, 513 in this direction would end somewhere around here, and as you can see, we have already run out of terrain. This is why you are getting this exception. So without going into too much detail about this, I'm just going to keep it simple. If you are setting x base and y base to anything other than 0, then make sure to reduce the size of the multidimensional array by that amount. So in our case, we have set x base and y base to 100, so we are going to reduce our multidimensional array size by 100. So change the value of rows and columns from 513 to 413 instead. And now when you hit play, as you can see, it works perfectly fine. It started from around this point and then went 413 in this direction and 413 in that direction. Now you already know why I'm setting refinement to 0.1. You can set refinement to any other value, and as you have seen in previous examples, different values will give you different results. The reason I've set multiplier to 0.01 is because the value returned by the Perlin Noise method is way too big to be used as terrain height data. So let's try setting multiplier to 1 and hit play. As you can see, the terrain is way up there. So to avoid this, we have to make the value much smaller, which is why we are setting the multiplier to 0.01. So yeah, that's it. I hope this video was helpful. If you want to check out more of my videos, head over to my channel, and there should be 2 videos up on the screen right now as well. Check out my music channel, DemkeysMusic. The link should be up on the screen right now. If you want to help me out with the donation, my PayPal email address is mentioned up on the screen and in the description down below. Don't forget to like, share, and subscribe. Leave your comments below, and I'll see you guys next time.